Who is undergrad? Okay. How many of you have taken differential geometry? Just a couple. Okay, that's good. So this talk hopefully will not require much knowledge beyond some calculus. So I'll be covering some differential geometry concepts, and hopefully one of the things you get out of this talk is you get a tour of some of the things that goes on in differential geometry, at least in low dimensions. I don't do any differential geometry above dimension 3. But if I start talking about something, you have no idea what I'm talking about, you should just stop me, and I'm happy to go into more explanations of what I'm talking about. So the thing I absolutely hate about math talks is I sit down, it's supposed to be an hour-long talk, 10 minutes in, I have no idea what's going on. Then the next 15 minutes, just like, oh, I guess I'm taking a nap now, I have no idea what's going on. So please, by all means, stop me if I start rambling about something you don't understand. So what's my background? So I'm actually a professor in computer science, not in math. But I've done a lot of things related to math my entire career. I do computer graphics, and in particular, I do the part of computer graphics that's physical simulation. So I work on taking the equations that come from physics and turning them into algorithms that can be used for doing things like simulating materials like cloth and hair and honey and so forth. And I'm also really interested in solving geometric design problems. Problems like, how do I make buildings that can stand up and have a certain shape and are made out of glass and steel? So, oops. So this is The Hobbit. How many of you saw The Hobbit? Yeah, I can't recommend it, unfortunately. How many saw Lord of the Rings? Lord of the Rings is the much better movie. But I do like The Hobbit because it actually used some of my stuff. So the hair and the fur on the different creatures in The Hobbit used some of my work on elastic rods. And then Disney movie, this is a Disney movie that came out a while ago, long before Frozen, called Tangled, about Rapunzel. And that used some of my work on cloth, on how to get the cloth to wrinkle and fold correctly. So what's going on here? Well, we're trying to simulate on the computer the behavior of these materials. And what is the main challenge? The main challenge is that when you study differential geometry, when you study most of mathematics, you're really studying things about smooth objects, or at least objects that are sufficiently smooth, C2. And when it becomes time to actually do things on the computer, this just does not work anymore. You have a finite amount of data, you have a finite amount of processing power, you have to represent everything discretely. So something that might look like a nice smooth teacup actually under the hood is represented as a very coarse grid of points and lines. And we have to somehow come up with a way of doing all the math that we need to do, solving all the PDEs that we need to solve on these discrete domains when you don't have sufficient regularity to just solve them as you would in typical smooth math. So how do you do this? Well, let's just start with the very, very most basic type of geometry you can think of, just 1D curves. Right? Everyone's familiar with 1D curves in the plane. Right? I've got some function parameterized by arc length, gamma of s. I can draw some tangent vectors at points along this curve, and I can draw some normal vectors at points along this curve. Now, why do I pick the normal vectors to go this way instead of this way? It's just some kind of arbitrary convention, right? Arbitrarily pick to rotate counterclockwise by 90 degrees to go from tangent to normal vectors here. But if I do this, I can now sweep along this curve, and everywhere I have my tangent vector, and everywhere I have my normal vector. Okay. Now I have a discrete curve. For a discrete curve, I just have some points and some lines. I don't have infinitely many points. Instead, I just have this piecewise linear thing, or I guess piecewise affine thing, if you want to be technical. Now, if I want to compute a normal vector somewhere like right here, this is not so hard, right? There's a clearly well-defined normal to put on this point here. But now what if I want to compute a normal vector on my vertex? Right? What do I pick? Do I just average these two normals? Maybe, right? It's not so clear. It's not so clear. Certainly you can't differentiate the tangent vector or do some business like this that you might try to do on a smooth curve to get a normal vector that appears here. Right? Okay, so how do we deal with this problem? I've got a curve. I want to do some geometry with this curve. Maybe the one thing you might think is, okay, I've drawn this curve, but this curve is not really what I have in mind. This curve is some approximation to some platonic smooth curve that I'm really thinking about, right? And the way I should think of this curve is one curve in a sequence of curves that have more and more and more points. And there are better and better approximations of this platonic smooth curve that I really have in mind. And when I ask to compute something like a normal vector of this curve, what I'm really asking about is a normal vector of this black curve here. Now, the problem with this is that there's no unique, well-defined way to go from here to here to here. I have to pick some rule for how to do this, right? It's kind of arbitrary. If I give you a cube and I ask, is this cube a sphere or a cube or a head or some other vaguely cube-like geometry, there's no canonical answer to that, right? So thinking of discrete curves just as one stepping stone on the way to a smooth limit curve is kind of a cop-out. The other problem is that you have to be careful about what is really going on when you take these refinement rules and get to a limit surface. Like this is a classic proof that you can find on Facebook. Someone who thinks they're very smart will post this to try to troll you and say, oh, pi should be equal to 4. And here's my proof. I can start with a square, and now I can refine the square so that I cut out the corners, and I haven't changed the perimeter of my square at all. And I can keep doing this process and get a better and better and better approximation to my circle. And it's going to converge to my circle in the limit of refinement. But my perimeter is still 4. So it must mean that the circumference of the circle is 4, right? And yeah, the point here, of course, is that the points are converging to the circle, but the tangent and normal vectors are not converging, right? They're staying aligned to the axes. So you have to be very careful, even if you do decide this is the road you want to take. You want to do this, think of these things as the curves on the way to a limit curve. You still have to be very careful you don't get trapped where the limit curve that you give is not one that you expect, not even half the properties that you expect. Now what's option 2? How many of you have taken some numerical math classes where you studied finite elements? Has anyone done that? Yeah, maybe, so the people in engineering definitely study finite elements. This is maybe the most popular way of doing all of these simulations. And the way that people do finite elements is they say, okay, I'm going to think of this curve. Erase it, so I'll draw it again. I've got these points. And the way I drew the curve before was by connecting them with lines. But I'm not going to think anymore of this curve as just being this piecewise linear thing. I'm instead going to think of these points as being some coefficients in some finite dimensional function space. So maybe I have a basis for my finite dimensional function space consisting of functions that look like this, right? And I can add together finally many functions that look like this and get some more general curves. And what I can think of doing then is saying, okay, if we've got these 3 points, really it represents some curve that looks like that, right? Where these 3 points I can just think of as coefficients in my space. This is a classic finite element approach to doing geometry. And the problem now again is, well, what subspace are you going to pick? What are your basis functions going to be? Again, there's no canonical basis to pick. And if you go to the building, the POB building, where all the people that do finite elements sit, they have all these heuristics for what finite elements to use for what problems. If you want to study collapsing bridges, you use this kind of element. If you want to study oil rigs, use this kind of element. And again, there's nothing canonical about the choice of these beats. And I consider this also a cop-out. What I really want to do is I want to treat this curve as the actual geometry. I don't want to think, oh, this is just some approximation, and I'm interested in the limit thing. I want to actually study this discrete object in its own right. And the advantage of this is that I don't need to worry about things not working until the limit of refinement. Anything that I have that works on any discrete curve will work no matter what I do to this curve, no matter what level of refinement I'm at. Okay, so when we look at 1D curves, really the only interesting piece of geometry about 1D curves is its curvature. Okay, if you've studied geometry before, even if it's in high school, maybe you remember how to calculate the curvature. You can take some derivatives of the curve, and that will give you the curvature at every point. Now the problem is, even the problem with this formula is in any case you need to take 2 derivatives of your curve for this formula to make sense, right? So already this formula is useless if your curve is piecewise linear, so just forget about this formula. Forget it. What is curvature actually? What is it? Maybe you have some idea. What is curvature? How would you define it if I didn't let you just write down a formula involving lots of derivatives?
Maybe easily something curves, perhaps?
Yeah, that's right. I mean, curvature intuitively is asking how quickly does this thing turn, right? Maybe we also added a sense of directionality to this. This actually turns out to be useful, right? Am I turning right or left? And if I am turning right or left, how quickly am I turning right or left? Right? So if I make the arbitrary decision that turning right is positive and turning left is negative, right? Then I have small positive curvature here. Curvature that's maybe still not quite zero. Zero would be just a straight line. It's very small over here. Then small and positive here, and then large and negative over here, and a sharp left turn. Right? Now, how can I formalize this ideal a little bit? Well, I can look at my normal vectors on my curve, and the speed at which these normal vectors are rotating as I move on my curve is measuring how quickly I'm turning. So what can I do? I can look at all of my normal vectors on my curve, and each normal vector I can just think of as a point on the circle. Right? It has just a direction, and that is a point on the circle if I just translate the vector to the center of the circle. And now, as I sweep along my curve here, I'm of course sweeping a path in space, but my normal vector is also sweeping a path on the surface of this circle. Now, what will this path here look like if I have very high positive curvature? If I have very high positive curvature, okay, I cheated because it's not even on the picture, so forget it. If I have very high negative curvature, if I'm down here, how will the path look like on the circle? Yeah, so for small motions along this curve here, I'm going to get large motions on my circle. And am I going to go clockwise or counterclockwise? Right, so if I'm over here, my normal is going to be over here. And then I'm going to quickly swivel to over here. Right, so I'm going to go counterclockwise. If I have small positive curvature up here, I'm going to move a small amount on my circle, and I'm going to move clockwise, right? What if I have a long stretch of straight line? What is that going to look like on the circle? Not much? Yeah. If I literally have just a line, straight line, and I move along here, what's the motion going to be on the circle? The point, right? The normal I draw anywhere on here is just pointing in the same direction. And all these map to the same point on this circle.
So is that kind of like a phase space?
Yeah, you can kind of think of it like that. So if you're taking physics, right, phase space is usually you think of both the position and the velocity of something, or the position and the momentum of something, right? You can kind of think of this somehow measuring the rotation, the angular momentum. There must be some nice explanation of this in terms of like a bead that's sliding along the line. And the way that its angular momentum is changing somehow corresponds to the curvature. There must be a good interpretation of that one. Okay, so now how do I measure the curvature? Well, let's say that I'm interested in the average curvature over some region of the curve. I walk along some region of the curve, and I measure the length of that patch, dl, and I look at how much of the circle here is also swept out by the normals, and I measure the length of that patch, dla. And now I declare my curvature to be this ratio. If I want my curvature at a point, I can just shrink this and see what happens in the limit, right? And this, yeah.
Is this equivalent to the formulation of curvature?
Oh yeah.
Okay, great.
Oh yeah. Maybe up to yeah. Maybe up to a constant. I don't know. Maybe up to a 2 somewhere. But I think this is actually exactly equivalent. Now the one thing here is that when I measure this length here, I'm usually measuring the signed length, right? If I'm sweeping a clockwise patch, I want dln to be positive, and I'm sweeping a counterclockwise patch, I want it to be negative. Right? That way I get positive or negative curvature depending on my curve is. Any questions about this? Okay. So now the fun begins. We have some understanding what a curvature is, and I now want to make a big list of all the different properties that you can think of that curvature satisfies. What are the invariants that curvature satisfies? What are the properties? What are the relationships of curvatures to other things? And we have our definition of curvature in terms of derivatives. We have our definition of curvature in terms of these ratio of this lengths on the curve and on the circle. What are some other properties of curvature? rigid motion to my curve and I measure the curvature, how will it change? Won't change, right? I can rotate my curve and the curvature at every point on the curve is the same. I can also translate that it's the same, right? So that'll be my first addendum to this list, is that it's invariant under isometries. And here I mean isometries of the plane, right? So I mean rotations and translations. What are some other properties of curvature?
The value of the point will only depend on that point rather than some infinitesimal neighborhood.
Okay, you're on the right track. What you say is actually not correct, right? The curvature at a point doesn't just depend on that point, right? It does depend on a neighborhood, but it only depends on a neighborhood. It doesn't depend on what's happening far away from that neighborhood, right? I mean, if I've got a point sitting in space, what's the curvature at that point? Who knows, right? It could be positive if the neighborhood looks like this, or it could be negative if the neighborhood looks like this. It could be 0 if it looks like that. I have to look at the neighborhood, right? But if this goes and does something crazy over here, who cares? Okay. But this is a great property, and we'll add to the list, which is that the curvature is a local thing. I can measure it based on just a neighborhood. What else? What happens if I reflect the curve? What happens to the curvature?
It's negative, I think.
It negates, right? Does that make sense to everyone? What else?
Scaling the curve by a factor of n scales the curvature by 1/n.
Yes. Does that make sense? If I have a tiny circle, the curvature there is very high and very quickly turning. If I have a huge circle, I'm very slowly turning. If I have an infinite sized circle, I just have a line. It's not turning at all. What else?
It's like a curve uniquely determined by its curvature at each point.
Yes. Curve uniquely determined by curvature. It's not exactly true, right? It's uniquely determined up to rigid motions of the whole curve, but more or less, right? Why is this true? Well, I just start walking along my curve. My curvature tells me how much to bend at every step, right? So I just walk and bend according to my curvature, and I trace out my curve. What else? We've got to fill the whole slide here. We barely have a first column. What else?
The sum of all, if you sum the curvatures over a closed curve, then that'd be 0.
Well, okay. Wow, this is a good. Okay, this is a good one. I like this one. Let's look at closed curves for a second. Here's a nice closed curve, imagining I didn't draw this incorrectly, right? Now I measure the curvature as I walk along this curve, and I integrate it all up, right? Integrate up my curvature. What am I going to get? There's a claim that I'm going to get 0. I don't really buy it, though, right? Because if I'm walking along this curve, it seems like I'm bending to the right a lot more than I'm bending to the left, right? In fact, if I just go around in a circle, I'm definitely bending to the right a lot more than I'm bending to the left. Right? So you're definitely onto something by suggesting to look at the total curvature. Who wants to guess what's happening here? What's the total curvature going to be?
Integer multiple of something.
Integer multiple of something. Yeah, that's right. Well, here's a question. If I go around a circle and integrate up my curvature, what am I going to get? How do I think about this? Well, let's go back to this picture, right? I'm going to be integrating this. I see the problem. This is wrong.
Yeah.
This is wrong. This should be dln over dl. Okay. Imagining this is corrected, this is dln over dl. If I'm integrating this up over my curve, the dl in the denominator cancels my dl, that's my integration form. And I'm basically integrating up how long is my path on this circle. Now if I'm just going around a circle, clearly the path I'm going to sweep out over here is just going to be the whole circle. And so what's my total curvature going to be? 2 pi. Now someone mentioned this integer multiple thing, and that's correct. How can I have a curve where the total curvature is 4 pi? Go around twice. Something like that. How can I get 0? Go around an 8. Yeah. Something like that. But it always has to be a multiple of 2 pi. You can prove this. It's a nice exercise in elementary differential geometry, but it's also obvious from the picture, right? If I have a closed curve, I'm going to start and end on the same point of my circle, and no matter what path I take, no matter how much I double back, I've got to paint the circle an integer number of times. So I imagine backtracking as negatively painting, erasing. Right? This, by the way, is called the Windy-Graustein theorem. It's also sometimes called the winding number theorem because this integer here is called the winding number of the curve. This is a good one, adding to the list. By the way, if I start deforming this curve, right, I'm going to be changing my curvature continuously, and I've got to be changing this number continuously, right? So something has to happen when I go from here to here, if I'm deforming my curve, when suddenly my total curvature jumps. And it's not so hard to see what's going to happen. This kink here is going to become sharper and sharper and sharper until I actually get something that looks like this. I get a singularity of my curve, and that's when my curvature jumps. It has to. There's no way to continuously smoothly deform these two curves and not have this kink happen. And the proof is that this thing has to change continuously, and there's no way it's going to go from 2 pi to 4 pi without singularity occurring. What else? Okay. Let me propose the following experiment. Let me draw another closed curve. Maybe this one will do. No, I'll draw a different closed curve. Now I'm going to pretend that this curve is made out of a rubber band. It's made out of a rubber band out of a material that really wants to shrink. And I want this material to shrink as fast as possible. Now what do I mean by this? I'm going to be drawing a vector field on here. And I'm going to be flowing my curve along this vector field. So I'm going to be shrinking it by moving it in the direction, each point in the direction of the vector that's attached to it. And I'm going to be looking at how this changes the area. And I want to draw a vector field, which, when I flow along it, causes this region to shrink area as fast as possible. Now, of course, I can just scale up all my vectors and I'll flow faster, right? So I'm going to have to put a budget on the integral of the norm of the vectors. I'm going to make that 1 or something, right? But if I don't let you just scale up all the vectors, how do you allocate, what vector field do you draw here that's going to make this shrink as fast as possible? What are your intuitions for that?
Largest vectors to be in the stretchest parts.
Well, how do I think about this? Well, here's an obvious thing, right? Anywhere you have a bulge that kind of goes out, like here, you're going to want to pull it in this way. And anywhere you have a bulge that bulges in, you're going to want to pull it in out that way, right? What do you want to do in flat regions? Well, I can apply a vector everywhere along this flat region that points the same way. This doesn't really accomplish anything. It's not going to change the length of that segment, right? And anything I do that's not just putting a constant vector everywhere is going to cause that part to be stretched, right? So really there's nothing productive I can do on this flat region. There's no point putting any vectors here. Put the 0 vector everywhere along this flat region. Yeah?
Why are you putting a vector to the outside, pointing to the outside on over there on that column?
So I want to shrink the length of this curve.
What, the
right?
length you're
Yes,
shrinking?
yes.
Okay.
I thought we were shrinking the area.
Oh, I misspoke if I said that. You could also do that experiment, and actually you'll get the same answer. But no, I want to shrink the length right now. So I want to pull this in, I want to push this out, and I don't want to do anything to this length here. And you can show that actually what you want to do is you want to assign a vector at every point, which is equal to negative the curvature times the normal at that point. I'm not going to prove this. It's too much of a tangent. You can do it on your own, and it's not hard. But the point here, the intuition here, is exactly what I said. If you have a big bulge, you're going to want to pull faster than if you have a small bulge. And if you have no bulge at all, you don't want to move at all. Now, the opposite also holds. If I want to increase the length of this thing as fast as possible, I want to move in the positive kn direction. So I'll add this.
Wait, really quickly. You said apply the 0 vector,
Yes.
but not the unit vector?
No, so I could do nothing to this curve, and then the length won't change, right?
Okay.
Or I could spend my budget to move this curve uniformly down, but what's the point? I'm wasting vectors I could be spending here, right? Yeah.
Why don't you try to move the points on the straight line towards each other? So towards the center with different speeds. Like
Okay.
towards
Yeah.
the middle, you slow down the shrinking process.
Well, here's the intuition. So my claim is that it never makes sense to have any component of the vector field point in the tangent direction of the curve. All this will do is reparameterize my curve without actually flowing it anywhere, right? So my claim is that we might as well only look at vectors that point orthogonal to my curve, right? So now if you buy this, right, then at the tips here I can apply a vector this way if I want, right? But it makes no sense to try and do something like this to this point here. You're just going to basically, if you imagine that I have some markers evenly spaced, evenly sampled on this curve, if I'm flowing in the tangent direction, I'm just redistributing those markers so that the markers are denser up here than they were originally. But I haven't actually flowed my curve at all. So something like this is a waste of budget. I always want to only move in the normal direction. And the question now is just by how much? And the answer is I want you to apply by the curvature. Other questions about this guy? I'm going to drop this in on my number 7. Now I'm going to say that what I mean, I'm going to call this the gradient of the air, of the length. I'm going to say that the length's gradient is the vector field Kn. Now, what does a gradient usually mean? The gradient means that I take a dot product with the gradient and it gives me a derivative in the direction of that vector, right? This is the gradient of the length of this curve in the sense that if I draw any vector field on here, and I want to know how much is that going to change the length, I can take the inner product of this vector field and this vector field, and I'll get the answer. So I get the biggest inner product if I take this vector field. If I do something tangent, I get 0. And I actually don't change the length of the curve at all. So I'm going to use like totally abused notation here to say gradient of area is equal to Kn. And hopefully this is somewhat reasonable to you. Last property I want to mention about curvature. I'm going to stick to closed curves. Now I'm going to look at the area. I'm going to call the area inside here A0. And now I'm going to draw the normal vector everywhere along this curve. And now I'm going to flow the curve in the normal direction to get a fattened area. So the distance anywhere here is epsilon. And I'll call the area that's inside the fattened area now A epsilon. Now my question is, what is A epsilon? how can I estimate A epsilon? I want to now expand A epsilon in epsilon, Taylor expand it. What am I going to get for the constant term? A0, right? I'm going to get A epsilon is A0 plus epsilon times something, plus epsilon squared times something. Clearly, the constant term is A0. I just plug in epsilon equals 0 and I get A0, right? Okay, what is the linear term? The perimeter, that's right. Call that out. Why is the perimeter the right answer? Well, I mean, you can imagine that the area I've added by extruding this blue region, right? I can think of it as more or less a rectangular strip, where the height of the strip is epsilon and the length of the strip is the perimeter, right? And I've kind of stretched and squashed this a bit as I've moved around. But to first order, the extra area here is exactly the perimeter. And now, what is the correction here? The quadratic term. Well, maybe we try an example. Maybe we try a circle. A0 is pi r squared. What's A epsilon? Well, okay, so what is this? Pi r plus epsilon squared. Even I can do this, right? Let's see. Pi r squared plus 2 pi r epsilon plus pi epsilon squared. Right? Okay. This 2 pi should make sense. This 2 pi r is exactly the perimeter. What is this pi epsilon squared? Maybe it's not so clear, right? What if I just have a line? Now you can say, okay, this is a bit cheating. It's not really a closed curve, right? Or if it is a closed curve, it's something that kinks super fast at the endpoints, right? But if I move the line up by epsilon, and I measure what's the new area, I haven't changed the area at all. It's still 0, no matter how much I translate this thing up and down, right? So in the case of the line, this term here is 0. So what's going on here? Well, you can show that the term that comes here is the total curvature of the curve, maybe with a factor of 1/2. Yep, there's a factor of 1/2 there. So, for example, if I had this infinity-shaped curve that we had before, and I were to flow this in the normal direction everywhere, right? Well, maybe this is kind of weird, right? Because if you start going around this thing, you see the normal doesn't always point in the direction you expect, right? It points in here and it points out there, right? But you can still start flowing this thing in the normal direction. You can calculate that when you do this, you have no quadratic correction. That's because the total curvature of this thing is 0. And you can calculate, if you don't believe me, you can calculate this and prove it yourself. It's again it's a little annoying calculation. You basically write down a formula for the blue curve and you calculate what its length is and you do some calculus. Okay, and then it turns out this is it. There's no cubic term, there's no quartic term, there's no other terms. You stop at quadratic. Does anyone have intuition for why we stop here? Well, if I take, so the next term I get here is the third derivative of the area with respect to moving in the normal direction. Well, the third derivative of the area is just the first derivative of this thing. And this thing is constant by the winding number theorem. So any more derivatives of this thing are just 0. now we've got our big list. There's a few things here I didn't mention because they're kind of trivial. I didn't want to waste time, right? Like, you can calculate what the curvature is explicitly for circles. This is not super hard. One thing I do want to mention is that if you have kinks in your curve, the curvature goes divergence, right? The sharper the turn, the bigger the curvature, and if you have a kink, then the curvature goes towards the right. Okay, now we have this big list of properties of curvature. And now we go back to the question of how do we discretize curvature on a curve that isn't smooth, but is chunky, it's discrete. What is our game plan going to be? Our game plan is forget this formula. This formula is useless because it has two derivatives, right? But some of the rest of these properties are not so useless. And we're going to use those properties as a way of coming up with a notion of curvature that doesn't start from this formula, but starts from the properties, and define our discrete curvature that way, and see what we get. Now, before I do this, I want to mention a bit about what does curvature even mean on a discrete curve. What does any function mean on a discrete curve? I mean, can think of curvature as just a function that assigns a value to every point on my curve. So if I've got a discrete curve, I'm going to call a function on this discrete curve just one number per vertex. I think I even have a slide for this. Yeah. So any function on my discrete curve is just a value at every vertex. And now, to do some of these things, like some of these formulas require me to integrate up curvature over the curve. How do I integrate up a function over a discrete curve? Who wants to suggest how I should do that? Add them, right? But I don't want to just raw add them. I want to actually take into account the fact that these edges have different lengths, right? So I'm going to associate a neighborhood to each vertex consisting of basically half the edge that comes before and half the edge that comes after. And if you ask me to integrate up something over the curve, I'm going to integrate up by doing a weighted sum. Right? What is this weight here? It's just measuring this half this distance plus half that distance. Everyone happy with this? Yeah? All right. Okay, so now we have some idea for how we should transfer over some of these properties we had before to the discrete case. So now let's do this. Which one should we pick to use as the basis of our discretization? Let's start with this guy. This is the winding number theorem, right? Total curvature should be a multiple of 2 pi. How are we going to discretize this? Well, let me go ahead and close this up. I'm going to take this property. I'm also going to insist on this property so that I now need to define a formula for calculating curvature at every point, and it shouldn't depend on things far away. It can depend on the neighboring edges. That's okay. That's the neighborhood in the discrete sense. But it shouldn't depend on things far away. And now I want to assign a number to every vertex here, so that when I integrate up in the discrete sense, the curvature, I'm going to get a multiple of 2 pi. How should I do this? Well, it turns out that if you want to do this, and you want to do it locally, there's really only one thing you can do, which is to measure the turning angle at every vertex. So I have to have some traversal direction. Let's say I'm going around this thing clockwise. So now I look at the turning angles. At every vertex. And these have to sum to a multiple of 2 pi. Right? Now, I can't just take the raw turning angles, because when I plug that into my weighted sum, I'm not going to get 2 pi because of the weights. Right? So what's the formula I should use for a curvature so that I get a multiple of 2 pi no matter what the lengths are of my edges? What's my formula? The curvature of vertex I should be what?
Triangle over the weight in the weighted sum.
Sorry?
The turning angle divided by the weight in the weighted sum.
That's right. So something like 2 times the angle, turning angle, over the neighboring edges. So now I multiply by the weights, I just get the turning angle, I sum those up, and I get a multiple of 2 pi. Does that make sense to everyone? Okay, that's my first formula for the discrete curvature. the isometry invariance property. If I rotate, the turning angle doesn't change, neither do the lengths, right? Scaling. The scaling behavior, you can see, is clearly going to be satisfied because if I scale, my angle doesn't change, but my lengths do, right? They change linearly in my scale factor. What about these more complicated properties, right? Well, maybe that's not so obvious what happens if I try to evaluate these more complicated properties using this curvature. So let's start over. Let's start from this requirement that the curvature times the normal is the gradient of the area, and see what formula we get from there. Maybe we get the same formula. We can check. So how do I do this? Well, let me draw a more simple object here. How do I calculate the gradient of the length as I move this point? Well, actually, in the discrete setting, it's much easier to do than in the smooth setting. In the smooth setting, you have to kind of hand wave. Or if you want to do it formally, you have to use the calculus of variations, which maybe some of you have seen already. If not, I definitely recommend taking a class in the calculus of variations. It's beautiful and it's very useful in any kind of physics that you want to do. But here, we only have a few variables that can change. We can change the positions of all these points, and that's it. And we want to know, well, in what direction do I need to change a vertex to increase the lengths of the segments as quickly as possible? What's the gradient of the sum of the lengths with respect to this vertex position? Well, the first observation is clearly moving this vertex doesn't affect those lengths here. It just affects the two neighboring lengths, right? Okay, and clearly the gradient of the length of this plus the length of this is the gradient of this plus the gradient of that, right? So what's the gradient of the length of this edge with respect to this endpoint? If I infinitesimally move this vertex in some direction, how much do I infinitesimally change this length? Well, it really depends which direction I move, right? Let me pick an easy direction. If I move in this direction, if I move parallel to the edge, how much am I going to increase the length of the edge? By that amount, right? That's easy. Now, maybe a little harder to think about is what happens if I move perpendicular, right? Now, if I move perpendicular, certainly I'm going to be changing the length. I'm going to be increasing it, right? But this increase is only a second order phenomenon. How do I know? Because moving in both directions increases by the same amount, right? That means I have to have a critical point there, right? So moving in this direction increases the length by the amount I moved. Moving in the perpendicular directions doesn't increase the length at all to first order. What does that mean about this direction? Well, the gradient of the length of this edge with respect to this endpoint is just this vector here, this unit vector here. If I want to know how much do I increase my length if I move in any direction, take the dot product of this with my test vector, and that gives me how much the length changes. Right? If I dot product this vector with itself, I get 1, which makes sense. The unit change in this direction changes by unit length. If I go in the perpendicular direction, the dot product is 0, and which makes sense because, again, there's no first order change in the perpendicular direction. Okay? So that's the gradient of this length with respect to this point. The gradient of the other one is just this vector here. It's again a unit vector pointing parallel to the edge. Right? Okay. What is my total gradient? Well, I've got to add these two vectors together. Right? And that is my total gradient of length. Move in this direction to maximize the change in length. Now, if I want to replicate this property here, this is just a direction vector. By the way, this gives me a definition of normal vector at vertices. Remember at the start, it wasn't so clear how to define it. Now we have a way. This direction now is a well-defined normal direction in this sense. But if we forget about the direction of this vector for now, the magnitude of this vector should give me the curvature, at least up to sign. Right? And the sign is kind of obvious whether it points out or points in. So how do I calculate calculate the length of this thing here. Well, I'm hoping someone will help me with the trig here. If I have a turning angle here, I've got the same angle here. I know that this length is 1. Well, I can't remember the proof right now for how to get the length of this thing here. There's some way to set up a right triangle that gives you that length, but I don't see it in the picture right away. But if you do the calculation, you'll get that the length of this vector here turns out to be the sine of half of the turning angle and I get this formula. For my curvature. So if I start from this formula as my starting point for discretization, I get a totally different formula. This is off by a factor if this has 2 sine and this has just the angle. Okay, well this is kind of annoying. If I start from different starting points, get 2 different formulas. Let's look at the last property, this inflation property. One question is, how do I even inflate a curve like this? How should I inflate it? There's no really right answer, right? There's 2 ways you might think of doing it. At least 2 ways you might think of doing it. You can inflate, well, it's obvious what to do when you want to inflate an edge, right? You're going to move along the edge by epsilon. So I can fill that in already. Now, what do I do when I want to inflate near the vertices? I mean, I can inflate just by filling in with circular caps, right? Now, every point on this inflated region has distance epsilon to the original region. And now what do I get for the terms of my expansion? Well, clearly I still have that the new region I've drawn with its circular caps is equal to the old area plus a bunch of rectangles and what's the total area of all those rectangles? Epsilon times the perimeter, right? So that matches so far. And then what do I get for this term here? Well, this term, the total area of all of these spherical caps has to equal this term here, right? And that means that the curvature here, well, this is epsilon squared times the fraction of the circle that is this piece of the circle here, right? And you can show that you recover exactly this formula. This perimeter is equal to this angle, right? And then you're scaling by epsilon. I get this formula. Now, by the way, this formula came from starting with the winding number theorem. It's obvious that the curvature defined in this way also obeys the winding number theorem. Why is it obvious? Well, if I add up all these pieces of a circle, clearly I'm going to get a whole circle. And if I have a more complicated shape, I'm going to get maybe multiple circles. So what's the situation here? The other thing you can do is you can fill these in. Instead of filling them in with circles, you can just extend the lines until they intersect. You'll get these diamonds that form. And if you show, you can show that if you do the calculation, you show that the extra areas you get at these diamonds gives you a formula involving the tangent of half the angle instead of sine of half the angle. Okay, fine. We now have 3 different formulas that we derived from the same set of properties. All of them obey the basic symmetries, like invariance under isometries. And we know that the different formulas, of course, were derived from these properties, so they must obey them, right? Now, what about the other properties? Well, we also know that this thing obeys the inflation theorem because we can interpret the inflation theorem in terms of spherical caps and get that, or circular caps and get that. Winding number theorem. It's not hard to convince yourself that this thing can't possibly obey the winding number theorem. You can add up a bunch of signs, there's no way you're going to get it. It's always a multiple of 2 pi. Same thing with the tangent formula. Gradient of length, I mean, there's only one answer to the gradient of length, and it's this formula. There's no way that these two also satisfy it, right? Inflation theorem, yeah, maybe there's a way to interpret this formula with the inflation theorem. It's not so clear to me. Maybe there's a different way you can inflate. Instead of using diamonds or instead of using circular caps that gives you the sine formula. So I'll declare this one unknown for now. Maybe there's a nice interpretation here. I still have one column left, and there's another property that wasn't listed before on this table, which is actually very useful for things like simulations, which is I really want the curvature to go to infinity when things become kinked. Why do I want this? Well, because a lot of the times the curvature is going to give me the energy of an object. And I want, if I'm playing around with a curve can bend a bit, but it really does not like to kink. It really hates it. I can't make it kink. I can make it close if I really push it hard, right? And I want this property to be replicated in my simulations. I want it to resist going through singularities. And which of these is going to have that property? That if the angle becomes too sharp, the energy goes to infinity, or the curvature goes to infinity. Only the tangent one. That's right. Okay, so what's happened here? So we're able to come up with discretizations of curvature. We came up with 3 different ones, and they all have their pluses and their minuses. I'm going to skip this. Forget it. Okay, what is the point here? The point is that if you want to discretize your smooth object, instead of trying to discretize these formulas, which you have no hope of doing because they have too many derivatives, you can instead look at the big list of properties and decide which are the ones that are important for your application, and then come up with what would the discrete notion of that have to be to satisfy that property. If I want the winding number theorem, what do I have to do to make the winding number theorem true? Right? And usually there's several answers. There's no one right way, one formula to use for this curvature of a curve, right? It turns out that the tangent formula is maybe the most popular in applications because of this property that resists kinking, right? On the other hand, evaluating tangents is more expensive than just evaluating the angles, so sometimes this is used instead. So there's trade-offs. And there's no free lunch usually. There's no one best way to discretize. Even for something as simple as a curve, there's no one way to discretize curvature that makes the most sense. It's all about which properties are important and which ones are not. Okay, I've got a few minutes left before the food arrives. So I'm not going to go through the whole thing for surfaces in space, but I'll give you some idea of how things generalize to surfaces. So I've got a surface now, and I can represent every point in the surface now, not just by a single function, but as a pair of function, or as one function of 2 parameters, and this gives me a point in space. Now the question is, what is curvature now? What is curvature on this surface? How do I measure it? How would you measure it if you had to come up with a notion of curvature for surfaces?
Try to fit spheres into the point.
You could try to fit some spheres to the point. It's not going to work so well, right?
Well, you could try fitting 2 spheres.
I see. Yeah, you can try to do something like that. You can try to fit spheres on both sides, or you can try to fit general conics, right? Maybe you'll get farther with that. You could try to do this, but let's do this. I'm going to give you 2 ways, 2 potentially natural ways to extend curvature in 2D to curvature in 3D. One of them is, well, okay, I'm just going to look at this point, and I'm just going to slice this. I'm just going to pick a plane and slice my surface and look at the cross section. And now my cross-section is a curve, and I can measure the curvature of the cross-section. Now it's going to depend on the orientation of the plane with which I sliced, right? So I'll just average over all the possible directions I could slice. And this is called the mean curvature. It's the average curvature of all the slices. So if I have something that looks like a sphere, right? If I have something that looks convex, like a sphere, every direction I slice is going to have the same curvature sign, right? If I have something like a saddle, I'll have different signs depending on which direction I pick to slice. What's the other natural way to extend it? Well, the other natural way is to take our picture of taking normal vectors and mapping them to the circle and do it to the sphere instead. So I look at a region of my surface, and I have a normal vector at every point, and I can map those normal vectors to points on the sphere. And I can measure, well, what's the surface area on the sphere? What's the surface area on my surface? And now I can take a ratio. just like I took a ratio of lengths in the 2D case. And if I do this, I get Gaussian curvature. And this time, this is also inverted. In fact, I got the wrong formula before because I copied this formula. And it was wrong here. So this should be the other way around. So we can look at some sample surfaces. If I have a saddle, the mean curvature, well, it's going to depend on exactly how the saddle is shaped. But if it's a nice symmetric saddle, the mean curvature is going to be 0. You're going to get curves that curve this way just as much as you get curves that curve that way when you take cross sections. Now, what is the Gaussian curvature? It's a bit tricky. If I draw a small neighborhood on my saddle and look at what happens on the sphere, if I go clockwise around my saddle, I'm actually going to be moving counterclockwise on my sphere. And so the ratio of areas here is going to be negative. If I look at the sphere, I'm going to get positive Gaussian and positive mean curvature. Every cross-section I take, I get the same cross-section, right? And clearly, if I map the normals of the sphere onto the sphere, I just get the region itself, right? Maybe scaled up depending on the size of my sphere. I'm going to get something positive for both curvatures. What do I get for this? What mean curvature and what Gaussian curvature? What mean curvature do I get? What sign? Well, I can pick a point here and I can slice, right? If I slice this way, along parallel to the axis of the cylinder, what's my curvature of my cross-section? 0. What if I slice this way? What if I slice any other angle? Still positive is slightly smaller, right? So if I average a bunch of non-negative things, I can get something positive, right? So this is positive mean curvature. What about the Gaussian curvature? If I draw a small neighborhood of my cylinder and map that onto the sphere, the normals onto a sphere, what do I get? It's not quite a point, right? Because the normal here is different than a normal here, right? But the normal doesn't change in this direction. So I'm actually going to get, yeah, an area 0 line, right? A curve on my sphere. So this has Gaussian curvature 0 and mean curvature positive. And the torus is more complicated. I'm not going into it. It varies depending on where you measure. 2 facts about curvature that are really important. The first is this Gauss's egregious theorem, which says that if you have a surface and measure the Gaussian curvature, and you deform the surface isometrically, the curvature doesn't change. Now, I don't just mean rigid motions of the surface. It's obvious that rigid motions are not going to change the Gaussian curvature. What I'm talking about here is motions that bend the surface without stretching it. So I can take this surface and I can roll it up in any which way I want. As long as I'm not stretching the paper, if I measure the Gaussian curvature anywhere, it's going to have to be the Gaussian curvature of the unfolded paper, which is 0, right? We already saw this phenomenon with the cylinder, which we measured as having Gaussian curvature 0. The other theorem, which generalizes something that was mentioned by one of you guys earlier, is that if I have the mean and Gaussian curvature of a surface everywhere, I know the surface, up to rigid motions. This is not obvious at all. This is deep as well. You have to solve some nasty PDEs to conclude this. But this is also true. Okay. The point now is I've got a discrete surface, and discrete surfaces look like this. Again, I have some points, I have some lines. Now I have some triangle faces that connect up the different vertices. And I need to measure curvature on this thing here. And if you look in a textbook and look up formulas for mean and Gauss curvature, there's no hope of applying them here. They're required taking 2 derivatives, right? So what's the game to play? Well, you can go through all these properties. I don't have time to explain these all. You can go through all the properties, and they have generalizations, including the inflation property. Now, the point is there's 2 different kinds of curvatures. So where before there was a single curvature, sometimes the mean curvature comes in, and sometimes the Gaussian curvature comes in. There's a bit of a splitting of roles here when you go from 2D curves in 2D to surfaces in 3D. But the inflation theorem still holds. Now you have several terms. You have that the volume is linear in the surface area, right? Makes sense. The surface area should be the first linear term in the expansion of volume. Then the mean curvature is the quadratic term, and then the Gaussian curvature is the cubic term. And if we want to discretize curvature, I'm not going to talk about this stuff. We can start with this formula here and see what happens if I inflate a discrete surface. Well, what happens? I take this discrete surface, I take a nice simple surface, and I inflate it. I get something that looks like this. How do I analyze this? What are the pieces, and how do they depend on epsilon?
The original thing.
Yeah, so inside the core of this thing is the original dodecahedron, right? And to this I've added some volume. How can I describe the added volume? What are the pieces?
There's 12 pentagonal prisms that are.
That's right. I've got some pentagonal prisms that are glued on to where the faces used to be, right? And what else?
Some cylindrical caps.
Yeah, I've got some cylindrical caps on my edges, right? And what else? I've got spherical caps on my vertices. I can even color them differently depending on what they are. Looks like this, right? These are linear in epsilon. These are quadratic in epsilon. These are cubic in epsilon. I think you're about to. Okay, so now I have a definition of mean and Gauss curvature. I measure these areas and I get formulas for what those are in terms of the different angles and the lengths. Now, there was this winding number theorem which says that every curve in the plane, if you integrate up the curvature, you get 2 pi. And there's an analogous theorem in 3D called the Gauss-Bonnet theorem, which says that if you integrate up the Gaussian curvature of a surface, you always get a multiple of 4 pi. Why 4 pi? Because 4 pi is the surface area of the sphere in 3D, just like 2 pi is the length of the circle. So for example, if I take a torus and I integrate up the Gaussian curvature, I'm going to get 0. Why do I get 0? Well, I need to look at, if I start drawing areas on here, look at how that maps onto my sphere. Just like for a curve, I can see that no matter how I move around the curve, I'm always going to paint the circle once, or a multiple number of times if I have something like a figure 8 or a loop-de-loop, right? If I start painting the sphere by mapping normals from this onto the sphere, I'm going to paint the sphere 0 times. I'm going to paint it once, and I'm going to anti-paint it once. So you can actually core this thing and see that here you have your once, and here you have your minus ones. And overall, I'm going to be painting my sphere 0 times. Now, the Gaussian curvature in the discrete case is the area of all these spherical caps. And my claim is that here I'm going to get 4 pi if I sum all these up. Why is this? Well, I totally did not spend half an hour last night making this animation.
Okay.
Worth it.
All right. So I'll show you some videos of the applications of this stuff. So you can take these formulas, and you can write down the physics in terms of these things, and you do things like simulate the physics of cloth. The physics of cloth only depends on the mean curvature squared of the surface. So if you can calculate this, you can calculate how the cloth evolves over time. I think this thing keeps spinning. Yeah. So I can make this thing keep spinning, and I can simulate how this thing interacts with itself in wrinkles and folds. And yeah, you can take a knife, you can cut through this thing, you can see the different layers of cloth that kind of piled up against each other, pushing against each other. And recently I've become interested in paper, in particular how paper crumples. And paper is the same physics as cloth, it's just a little thinner and a little stiffer. So one thing I'm really interested in is how paper cones crumple. So I'm going to do a demo. It's always dangerous to do a live demo, but I'm going to try it anyway. I can take a cone of paper, and I can take it and I can jam it into a hard surface. This one kind of worked. You can try to pass this around. Let me try it again. So I brought multiple cones. This one worked less well, but you can kind of see what happens on the tip.
Yeah.
That one was the best. Okay. Well, I'm not a physicist in a laboratory. laboratory. If you're a physicist in the laboratory, you can do this experiment. You get something that looks like this when it comes out. In fact, I can show you what it looks like before you cut it open. You take your cylinder, you crush it using a piston into a table. You pop it back up, and you see this diamond pattern that's formed of crumplings of this paper. The physicists have no idea why this happens. I have no idea why this happens either. I tried to simulate this, and I got the wrong answer. So I'm working right now on what's the right representation of paper. How can I represent the geometry of what's happening here in a way that I can predict what happens here and tell the physicists, oh, it's because of the air pressure inside. Or, oh, it's because of the thickness of the paper. Turns out neither of those are the answer. I tried both already. But, okay, yeah, this is the current version of my simulation. So I can simulate this crumpling process, and I can look at the mean curvature of my crumpled cone. And the regions here are where the mean curvature is high, so where there's been creases in the paper. And it kind of looks like diamonds, but it's nowhere near what actually happens in the paper. This is something I'm currently trying to improve on. Okay, yeah, that's all I'm going to say. Okay, so thanks a lot for your attention. I hope you learned something new. Do you all have questions? All right. Well, allegedly there's pizza somewhere, so.
I mean, the person who orders pizza from